Hello everyone, my name is Ivan Fernandez and this is my colleague Pablo Gonzalez and we are here to present our project on the numerical analysis of the Airy equation. In this project, we analyze the linear dispersive Airy equation, given by the first equation in the slide. We are solving this equation in a domain from -1 to 1 using periodic boundary conditions. For initial condition, we have chosen a superposition of two cosine waves. Our main goal here is to analyze the numerical behavior of this problem using time integration schemes.
We have established four main objectives for this study. First, we aim to analyze the stability of various one-sided four-point distances. Second, we want to identify which of these schemes are stable when using the explicit Euler method. Third, we will demonstrate the inherent stability of the classical five-point centroid stencil. And finally, we will attempt to recover stability by applying two different methods, adding a standard diffusion term versus adding a superdiffusion term. To perform our theoretical analysis, we use the Von-Neumann stability method. This involves calculating the amplification factor denoted here as G, which depends on the time step and the Fourier symbol. For the explicit Euler method that we are using, the scheme is only stable if the modulus of this amplification factor is less than or equal to 1. Geometrically, this means the eigenvalues of our spatial operator must lie inside the stability cycle of the Euler method in the complex lane.
Let's look Let's look at the first asymmetric scheme, the full upwind stencil. When we analyze the Fourier symbol, we see that the real part is strictly positive. This is problematic because positive real parts push the amplification factor outside the stability region. As a result, the condition model G is bigger than 1 is always true, meaning this scheme is unconditionally stable for any time step. Next, we analyze the biased stencil using 2 points upwind and 1 point downwind. This case is different. The real part of the Fourier symbol is negative. This places the eigenvalues in the left half of the complex plane, which allows them to fit inside the stability region of the Euler explicit method. Therefore, this scheme is conditionally stable provided that we satisfy a specific CFL condition, where delta t scales with delta x cubed. We then checked the reverse bias, 1 point upwind and 2 points downwind. Similar to the full upwind case, the real part of the eigenvalue here is positive. Consequently, the magnitude of the amplification factor is always greater than 1, making this scheme unconditionally unstable regardless of the time step selected. Finally, for the full downwind stencil, the eigenvalues trace a circle that extends outside the stability region of the Euler explicit method. Even though the real part can be negative, the curve itself does not remain within the required stability boundary. Therefore, this method is also unstable. Here we can see the numerical results confirming our analysis. If you look at the plots from completely upwind, one up to down, and completely downwind, you can see that the solution is unstable. However, looking at the top right graph for the two up, one down stencil, the simulation is stable and matches the exact solution, although it does introduce some artificial damping.
Now we move on to the 5-point center stencil. In CFD, we usually prefer center schemes because they don't introduce artificial dissipation. However, for this equation, the Fourier symbol is purely imaginary, because the explicit Euler stability region does not include the imaginary axis, except at the origin. The amplification factor is always greater than 1. This theoretically proves that the central scheme is unconditionally unstable. We verify this theoretical instability with numerical tests. As you can see, this plots, the solution explodes into high frequency noise. We tested, we tested progressively smaller time steps, going as low as 10 minus 8. In every single case, the simulation eventually blew up, confirming that you cannot use this stencil with explicit error without modification.
To fix this, we need to add a stabilization term. We performed a truncation error analysis and found that the leading error of our scheme is of order delta x squared. This is crucial because any artificial viscosity we add must scale with this error, leading error, or smaller. Otherwise, we would degrade the accuracy of the solution. We propose two methods. Method A using standard diffusion and method B with super diffusion scaling with minus u x x x x. This slide compares the results at time t equal to 0.03. The top plot shows the unstable center scheme exploding. The middle plot shows method A, standard diffusion. As you can see, it fails to stabilize the solution and the practical time steps. The high frequency noise is still dominating. The bottom plot shows method B, superdiffusion, which successfully suppresses the instability while preserving the smooth shape of the wave.
We can quantify this performance by looking at the L2 error. At t equal to 0.03, the central schemes and method A are completely diverse, with method A showing a massive error of 2.58 plus 10 elevated to 12. In contrast, method B, the superdiffusion, remains stable with a very low error of approximately 0.029. This proves that superdiffusion is the only effective strategy here. To conclude our presentation, first, the standard center stencil is unconditionally stable for this problem. Second, while the asymmetry 2 up, 1 down stencil is stable, it is dissipative. Third, standard diffusion is inefficient because it requires impractically small time steps to prevent blow-up. Finally, superdiffusion is the most robust method. It stabilizes the scheme at the standard time step and preserves second-order accuracy by effectively damping high-frequency noise.